So we're going to continue working on head laws in different regime of the fluid flow. The other regime of the fluid flow that we have is turbulent flow. Turbulent flow inside the pipes or ducts or channels. Turbulent flow is characterized by disorderly and rapid fluctuations of swirling regions of fluid that are called eddies throughout the flow or vortices. These fluctuations may provide an additional mechanism for momentum and energy transfer. In turbulent flow, the swirling eddies and vortices transport mass, momentum, and energy to other parts of the flow much more rapidly than molecular diffusion mechanism that we have in laminar flow. So greatly enhancing mass, momentum, and heat transfer. So we have better heat transfer and momentum transfer and mass transfer in turbulent flow than laminar flow. As a result, turbulent flow is associated with much higher values of friction factor. So friction is larger in turbulent flow. If you have turbulent flow, we cannot, and we have circular pipe, we cannot use the equation that we had for Darcy friction factor in laminar flow that was 64 over Reynolds number. Here, our equation is different. It's a little bit more complicated to calculate. This is called this is one of the equation, the Kohlberg equation that we may use. But the problem with this equation is if you want to use it, you need to keep in mind that you have F at both sides of the equation. So you have implicit form of equation for F. As an alternative, instead of this equation for the calculation of Darcy friction factor for turbulent flow, for internal flow when your Reynolds number is larger than 4,000, you can use Holland equation. Holland equation is easier to use because it is in explicit form. So you have F only on the left-hand side. This is a good approximation. This equation is a good approximation of this equation. So here, look at different variables that you have. So at the left-hand side, you have 1 over a square root of Darcy friction factor. F must be calculated. At the right-hand side, you have log. So the base for this log is 10. This is not natural log. So base is 10. Make sure when you are using your calculator, keep in mind that you are using log with the base 10. Negative 1.8 times log 6.9 over Reynolds number. So you need to calculate the Reynolds number plus what is epsilon? Here D is diameter, obviously. Epsilon over diameter divided by 3.7 all to the power 1.11. The epsilon is the roughness of the pipe surface or the channel surface or the duct surface. This is the roughness and has a length scale. So it is in meter or millimeter or centimeter. So you need to know that and you need to read that based on type of the duct from the appendix or sometimes is given in the problem statement. Epsilon over D is called relative roughness. So the friction factor is fully developed turbulent pipe flow depends on the Reynolds number and the relative roughness. By the way, when I say channels and ducts, please keep in mind that these equations are only valid for circular pipe. We just, for now, we're going to use it for circular pipe. So here, we already solved for laminar flow. Now I want you guys to solve this problem that is very similar to the previous example that I solved for in the video for Tuesday's session for laminar flow. So here, you need to deal with the different regime of the fluid. Water at 158 degrees Celsius and density of 999.1 and dynamic viscosity of 1.138 times 10 to the negative 3 is flowing steadily in a 30-meter long and 5-centimeter diameter horizontal pipe made of stainless steel at a rate of 9 liters per second. What is the pressure drop, the head loss, and pumping power requirement to overcome this pressure? So obviously, again, you need to define your regime of the fluid flow first. Then you need to choose the equation that you need to use to calculate your Darcy friction factor. You need to see if it's turbulent or laminar. If it's turbulent, then you need to use one of these equations. And my recommendation is to use this equation, not this one, because here, this one is easier to calculate. If it's laminar, then you want to use different equation that was this. So first you need to define your regime of the fluid flow, then calculate the Darcy friction factor, and then follow the same procedure, similar procedure that we followed, that we did in previous example to solve for these 3 quantities. So the question here is where these equations are coming from. These equations are basically coming from Moody chart or Moody diagram. This is simplified or form of Moody diagram. Moody diagram have different regime, different parts: laminar flow, transitional flow, and turbulent flow, and fully rough turbulent flow. This is a more detailed or actual form of Moody diagram. So you can use the Moody diagram to calculate your friction factor for turbulent or laminar flow. But since you have already access to the formula and correlation is really easier to calculate. So just use these equations or 64 over Reynolds number if you have laminar flow. Example. The water needs of a small farm rate are to be met by pumping water from a well that can supply water continuously at a rate of 4 liters per second. The water level in the well is 20 meters below the ground level, and water is to be pumped to a large tank on a hill, which is 58 meters above the ground level of the well, using 5-centimeter internal diameter plastic pipe. The required length of piping is measured to be 420 meters, taking the efficiency of the pump to be 75%. What is the rated power of the pump that needs to be purchased in kilowatt? The density and viscosity of water at anticipated operation conditions are taken to be 1,000 kilogram per meter cube and 0.00131 kilogram per meter second, respectively. So the density and viscosity is also given. By the way, you need to look at the unit and see if it's dynamic viscosity or kinematic viscosity. This is the kinematic of the problem. This is the schematic, I'm sorry, the schematic of the problem. The density and dynamic viscosity, it was actually dynamic viscosity. The dynamic viscosity are already given. So again, this is very important to look at the unit and see if you are given the dynamic viscosity or kinematic viscosity. mu or nu. Now, here, this is a schematic of the problem, the reservoir and the wall and the piping and the pump in between. The density and dynamic viscosity, as I said, are given. The chosen point, we choose 0.1. We choose 0.1 at the free surface of well water. So this is 0.1 at this surface, and 0.2 at the free surface of the reservoir in the farm. The fluid, we notice that the fluid at both points is open to the atmosphere. It means the P at 0.1 at this surface and 0.2 are equal and are pressure of the atmosphere. So P1 is equal to P2 is equal to pressure of the atmosphere. Velocities at 0.1 also, because we assume that the free surface of the well, the free surface of the reservoir and free surface of the well does not really change. So the velocities at those points are assumed to be zero. So these levels, these free surface level here and free surface level here at the well and at the reservoir do not change significantly. So the velocities at 0.1 and 2 are also equal to 0. We take the free surface of the wall as the reference level. So here is Z1 is equal to 0. And then the energy, we write the energy equation for a control volume between these 2 points that is simplified to this equation. So this is the energy equation. We don't have turbine, so we don't have this term. This is 0. We have pump. We have head loss as a result of piping. So, and also pressure at 0.1 and 2 are 0. Are equal or not 0. Are equal is equal to pressure of the atmosphere. These two terms cancel out. Velocity at 0.1 and 2 are almost 0. Z1 is equal to 0 because this is where we assume to have to be a reference level. H turbine is 0, so the simplified form of the energy equation for control volume between the points 1 and 2 simplified to this form. This is a simplified form of the energy equations between point 1 and 2. So if you want to calculate the pumping power required, we need to calculate the head loss. We already know the Z2 because Z2 is 58 plus 20, that is equal to 78 meter. Now, to calculate the head loss part, we need to use this equation. F Darcy-Weisbach friction factor times the length of the piping divided by the diameter of the piping times the velocity squared over 2G. Over 2G. So if you want to use this equation, you need to know the regime of, you need to know Darcy friction factor F. If you want to calculate or know the F, you need to know the regime of the fluid. That means we need to calculate the Reynolds number. So this is what we need to do. Calculation of the Reynolds number, defining the regime of the fluid, whether it is turbulent or laminar. If it's laminar, then we need to use certain equation. If it's turbulent, we need to use different form of equations. Now for F, then we plug the calculated F into here and calculate HL, and then from there we calculate the pumping power requirement. So the first step is to calculate the Reynolds number. To calculate the Reynolds number, we need to know the velocity. To use this equation, rho VD over mu. This is dynamic viscosity that has a unit of kilogram per meter second in SI unit. Velocity is volumetric flow rate divided by the cross-sectional area of the pipe. Volumetric flow rate is 4 liters per second, or 4,000 meter cube per second, divided by pi d squared over 4. This is velocity. And from here, we calculate the Reynolds number. Reynolds number is 77,750. It means it's larger than 4,000 and it is turbulent. The regime of the fluid flow is turbulent since Reynolds number is larger than 4,000. So now we need to calculate the friction factor. The friction factor can be calculated from the Moody chart or Kohlberg equation or Holland equation. So we may use these, but as I said, in this chapter, we just want to use the equations. We use these two, either one. Turbulent, we can use the Kohlberg equation or Holland equation. This is easier to use. As I said, this is a very good approximation of the Kohlberg equation. It's easier because we only have F on the left-hand side, so it's in explicit form. If you use that equation, the Holland equation, the F is around 0.01897. This is the value that, this is a value of the Darcy friction factor that actually I calculated using the first equation. But even if you use a Holland equation, you're gonna get the very similar value. So if you use this equation, you're also gonna get value very close to this one. But this is what I calculated using Kohlberg equation. Now that I have Darcy friction factor, I plug that in to the equation for the calculation of the head loss. So this is what I did. The unit of this is meter. This is very important. So the unit of what I get from this head loss equation, if I use all the SI unit, will be length scale in meter. 33.7. So the head loss for the head loss or the head pump head requirement will be equal to Z2 plus HL according to this equation that we derive from energy equation. 78 plus 33.7 is equal to 11.7 meter. So this is the head requirement for the pumping power for the pump. Now, what is the pumping power? This is the head of the pump. If you want to calculate the pumping power, what you need to do is multiplying the volumetric flow rate by rho density times G times the pumping power. So you remember in another example, when we wanted to calculate the pumping power, what we did was multiplying the volumetric flow rate by the pressure drop. Here, since we don't have pressure drop, we have a head loss. What we need to do is multiplying the volumetric flow rate by rho density times G times head. This part, rho GH, gives me a pressure unit. When I multiply it by volumetric flow rate, it gives me power unit. But also in the problem statement, it says the pumping has a certain efficiency. So I need to divide it by the efficiency of the pump. And this would be pumping power requirement for this piping, for this system. What I want you guys is to solve for the previous example as the practice for this session, to solve for this practice for the previous example, with the only difference of having flow rate of 0.04 liter per second, and see what procedure you need to make. You need to follow the similar procedure, what value you get for the pumping with the same efficiency, all the variables, so the same problem statement. The only difference here is instead of 4 liter per second, your flow rate or volumetric flow rate is 0.04 liter per second. Thank you. And thank you.